All right, these are the answers to the vector breakdown and circular motion. Letter A says, calculate the weight of the brick and add it to the diagram. So plug and chug, W equals mg, and the earth is always pulling down. And so this weight equals 22.25 newtons. Okay, and then I already drew the tension on the rope. Remember that ropes always pull in, so you can see it's pulling up on the brick, which is towards the center of the rope, and pulling crooked on the tennis ball. But both of those tensions are pointing towards the center of the rope. Okay, and then it says draw the weight of each object on the diagram. So the tennis ball also has a weight. Since these aren't the same, these technically should have subscripts, weight 1 and weight 2. Oh, it doesn't say calculate the weight of the tennis ball. I know you can do that. That is W equals mg. It's in the paper answers. So 0.585 times 9.8 equals 5.733 newtons. Okay, then you can see that I drew the plane of the circle that the tennis ball is going in. And all right, so A is calculate the weight of the brick. B is draw the weight of each vector, of each object. C is break down the tension vector on the tennis ball into horizontal and vertical components. Okay. All right. I was going to say, this didn't walk you through. Okay, then they tell you, I tell you, since the brick is in equilibrium, the forces are balanced, right? This is not moving up and down or going in a circle. So the tension in the rope is equal to the weight of the brick. So this blue tension, because these two forces are balanced, is equal to the weight of the brick, which is why we calculated that. And all of these rope molecules are evenly stressed. So now we know that this blue tension up here, I'm going to draw this bigger. This tension is 22.25 newtons because these rope molecules and these rope molecules are stretched by the same amount. And then the weight of the tennis ball is 5.733 newtons. And then we don't know what the angle is yet, it looks like. Okay, it says break down the tension vector into horizontal and vertical components. Okay. So if you remember, this is our coastline. So we don't know theta, but whatever theta is, this is 22.25 times the cosine of theta. And the vertical is 22.25 sine of theta. Okay, so this problem's a little abstract because we don't know what theta is yet. Okay, so we did that. We drew the weights. We broke down the tension vector. And then D says set up the non-radial column for the tennis ball to find the angle. Okay, non-radial means not in the plane of motion. Okay, so actually let me talk about the radial. In must win. This is the center of the circle. You have to have a force pointing towards the center. And hopefully you can see it is this part of the tension, the crooked tension, the 22.25 cosine of theta. That's what's pulling the tennis ball in over and over and over again. All right, but you have to figure out what the other two forces are doing. This upward part of tension is balancing the weight. So that's what we're doing, is we're going to set these two forces equal to each other. That's what's non-radial or not in the plane of the circle. Okay, so non-radially, the sum of the forces equals m A, but A is 0 because the tennis ball isn't moving up and down. And so we have the 22.25 times the sine of theta minus the weight of the tennis ball. Nobody's winning because the forces are balanced. Okay, I'm going to add the 5.73C33 to both sides. And then we're going to divide by 22.25. And you get sine of theta equals 5.733 over the 22.25, which is 0.258, which is good that it's less than 1, right? Because sines of angles have to be, the biggest they can be is 1. Okay, and so theta is inverse sine of 0.258, which is 14.93 degrees. All right, so if you get something other than 14.93, check the mode in your calculator. You're probably in radians. Okay, awesome. Now that we know theta, we can go up here. This is 14.93. Now we can figure out what this inward pull is. The inward pull is 22.25 cosine of 14.93, which is 21.5. Check that out. Okay, so we use the non-radial column to find theta because we knew everything else. Now we plug theta back in, and now we know that the force, the part of the tension that's pulling inward, is 21.5. It's really, really close to the actual tension. That must be a much shallower angle than I drew. All right, so now we know the only radially inward force is 21.5. Okay, your radial column will always start with sum of the forces equals mv squared over r. And then you're going to do all of the inward forces minus all of the outward forces equals mv squared over r. You don't have to have an outward force. So this tension horizontal is winning by default. And we just figured out that that inward component was 21.5 newtons equals the mass of the tennis ball, not the mass of the brick, times v squared. We're trying to figure out how fast we have to spin it in order to make it go in a circle. And then the r is kind of a little bit complicated here. I'm not going to put anything that complicated on the test. I just wanted to give you some real numbers to go with the demo so that it had some context. So if you see the radius of this circle is 0.5 cosine theta. This dimension here is 0.5, and therefore the radius is 0.5 times the cosine of theta. It's just vector breakdown like we've done before. Okay, so the radius is 0.5 cosine of, and theta we now know is 14.93. Okay, so then that gives us 21.5 equals, take 0.585 divided by parentheses 0.5 times cosine of 14.93, and you get 1.21. Divide both sides by 1.21. And you get v squared equals 17.77. Take the square root of both sides, and you get that you need to be spinning the tennis ball at 4.22 meters per second. That's about 9-10 miles an hour. So not super fast. Okay, so that one was kind of complicated because of not knowing theta. That was a little bit more challenging than what will be on your assessment, but still good practice. Okay, so this is the olive in the Brandy Snifter demo, and I tried to take real dimensions. Again, I like to highlight the circle that the object is going in, and that way you can see the normal force. Part of it is literally pushing the olive towards the center, and part of it is balancing the weight. Okay, this is exactly the same force diagram as when you do your flying pig lab, except that the normal is tension. But hopefully you can see the similarity between this force diagram and this force diagram, the exact same force diagram, except normal and tension are you either have normal or tension. Okay, and then you have a bunch of dimensions here. Okay, so it says use the non-radial column to determine the normal force. So the olive is not accelerating, so some of the forces equals 0. And so we have up forces minus down forces. We have n sine of 22 minus the weight equals 0. And let's go to our miscellaneous column. You can do it all here if you want. I'm just trying to make things a little bit cleaner. So again, I tried to make these numbers realistic. A 0.4 gram, no, 4 gram marble, so that's about 4 paper clips, has a weight of 0.0392 newtons. Okay, so n sine of 22, I'm going to add a weight to both sides, equals the weight. I'm going to divide both sides by sine of 22. So the normal force equals 0.0392 newtons. We're going to divide by something less than 1, right? Because sine and cosine are always less than 1. So we should get a bigger number. That should make that go up. So it went from about 0.04 to 0.10464 newtons. Right? Small because we're talking about a marble. Okay, awesome. So that is the normal force. And now we're going to use the radial column to determine the speed of the marble. So your radial column is always the sum of the forces equals mv squared over r, in minus out. You only have one inward force. You have this n cos 22 equals mv squared over r. We found the normal force. So that is, let's use, so 0.10464 cosine of 22 equals 0.004 v squared over that teeny tiny radius, because it's in meters. Okay, I will calculate some of these numbers. Okay, so the 0.10464 cos 22 turns into 0.097. This stuff turns into 0.066. I'm going to divide both sides by 0.066. And you get v squared equals 1.47, and take the square root of both sides, and you get that the velocity of the marble is 1.21 meters per second squared. Okay, and then question C, calculate the circumference of the circle. Circumference is 2 pi r. I will give you that equation on the test. So this is just kind of plug and chug. I guess so that we can do the next question. So the circumference is 0.380 meters. And I guess I did this so that we could figure out whether this was correct. Use the speed of the marble and the circumference to determine the time it takes for the marble to make 10 complete revolutions. Okay, so we're going to use distance equals rate times time. Sometimes people are like, what is that? I guess maybe you don't see that as much in math. So I will then instead write it as, this is the position function with x naught is 0, no acceleration. We're going to assume that the speed is constant. So the distance we want to travel is 10 revolutions. So 10 times 0.380 meters, that's the distance we're going. And the speed that we calculated was the 1.21 meters per second. And we're looking for time. Okay, and so you divide both sides by 1.21. And you get the time is, ooh, look at that pi. That is a coincidence. So about 3 seconds to do 10 revolutions. That's pretty fast, but I guess if you remember the demo, maybe that makes sense. So let me know if you want to try it in class. All right, I think this is the last question, and again, we will see that it is very, very similar. We are going to draw the forces. Let's see what's going to show up here. We must never forget this. Okay, so the swing ride person has weight. The mechanical force is spinning the ride, but it's not touching the person. Technically, the person has a normal, but we're going to treat the person and the like seat as one solid thing, and so we're going to say it's tension, not the normal. There's no friction, but there is tension in the rope, and the tension you can see is crooked. So this is the circle that we care about. So I'm going to draw this over to the side. So the weight is perpendicular. So don't confuse weight in a roller coaster ride problem where the weight is pointing radially outward or radially inward. It's in the plane of the circle, right? Hopefully that makes sense. Here's your circle that you're going in. If you're going in a loop-de-loop, the weight is in that plane. Here, the weight is perpendicular to that plane. So do not memorize, that weight is always perpendicular to the circle and doesn't go in the radial, because for vertical circles, it does. Okay. And then this is t cosine of 30, because it's a coastline, and this is t sine of 30, because it's a stop sign. Okay, so determine the tension in the cable. It does not say where to get that from, but we know the weight. So we know that this upward part of tension is balancing the weight. So we're going to go in our non-radial column, and we're going to say the forces are balanced. The person is not accelerating up and down. So T, not all of the tension, just like a lawnmower suitcase, only part of the tension minus the weight. Nobody's winning. The person is not moving perpendicular to the plane. Okay, so then T sine of 30 minus 176 times 9.8 equals 0. And up here, T sine of 30 equals, I'm just going to do that out. You get 1725 newtons is their weight. And then you divide both sides by sine 30. So you get tension is 3,450 newtons. That's a lot because it's a real ride. It's not supporting a marble or a tennis ball. It is supporting a massive ride. Okay, then question C is determine the tangential speed. And speed is all about the radial column because it's mv squared over r. So part of the rope, this green part, is pulling the rider inward towards the center, so that is positive. So we have sum of the forces equals mv squared over r, in minus out equals mv squared over r. You don't have any outward forces. You have t cosine of 30 is pulling the rider inward over and over again. We just found the tension. So 3450 cosine of 30 equals 176 v squared. They gave you the radius of the ride was 13. This turns into 2988 equals 13.54 v squared. Divide both sides by 13.54. And you get v squared equals 221. Take the square root of both sides, and you get 14.9 meters per second. So that's about 32 miles an hour. So that's pretty hefty. That's pretty fast. All right, so moral of the story is weight will always be balanced by the upward part of the force, and then the horizontal part is always what's helping you turn. Okay, so if you go back and look at these three, it's the same force diagram over and over again. I just happened to start with the hardest one because you didn't know theta and you didn't know the radius. Okay, but it's the same force diagram, the same process. It just depends on what you know and what you don't know. All right, thank you for listening, and I will see you in class.